Hi everybody and welcome to this 9th video of BIOB20. In this video I would like to talk about transforming Gaussian distributions. We have seen how to use the function rnorm to generate Gaussian random numbers. For instance, rnorm equals 5. Now if I'm interested in the square of Gaussian random variables, I can use the square symbol, which is ℏ2, following the rnorm n equals 5 function, and I would get the square of 5 Gaussian random numbers. To know what the distribution of the square of a random Gaussian distribution looks like, we're going to create a relatively large sample of 100,000 Gaussian random numbers that we're going to raise to the power 2. If we now look at the histogram of this distribution, we see that this is very asymmetric, that of course the values cannot be lower than 0, and that most of them are actually close to 0 and very few values are above 10, for instance. Another way to represent this distribution is to use the function density, which is essentially a continuous version of the histogram. We obtain a graph that has the same shape as before, except that the collection of bars has been replaced by a single smooth line. Note that the y-axis does not show the counts anymore, but an arbitrary density function. It turns out that this density is actually a gamma distribution. To show this, we are going to sample a gamma distribution with a large sample size. Importantly, I'm setting shape to 0.5 and scale to 2. Then, to add a new line to the existing graph, I'm using the lines function, and I'm passing the density of y with color 3 for green. And as you can see, the two densities are exactly identical. That shows that indeed squaring a Gaussian random variable is the same as taking a gamma distribution with shape equals 0.5 and scale equals 2. What about the sums of squared Gaussian random variables? In this example, we're taking 5 random Gaussian numbers, we square them and sum them so that we obtain only one number. If I want to do this a large number of times, I need to use the function replicate. I create a new sample x where I use the function replicate with n equals 100,000, and I use the expression that I've just defined before. When I plot the density of x, I get a new shape that is slightly different from the previous one. And we can see that indeed it no longer coincides with the gamma distribution that we had made before. Instead, it coincides with another gamma distribution where we change the shape parameter. I update the shape parameter to 5 times 0.5. If I do this and I overlay the density with the red color, you can see that now the two densities coincide exactly. This particular gamma distribution is known as the chi-square distribution with 5 degrees of freedom. The degrees of freedom of the chi-square distribution is equal to how many Gaussian random numbers you have summed to obtain one number. This is 5 in that case. In summary, the chi-square distribution can be seen either as a sum of squared Gaussian random variables or as a special case of gamma distribution. Next, I would like to talk about logical operations. To have something to work with, we are going to create a random sample from the Poisson distribution. We have seen previously that we can select from a vector using the square bracket notation. If I want the elements above 1830, I say x square bracket, x greater than 1830. The mechanism of this selection procedure is that x greater than 1830 gives a true-false vector, also known as a logical vector. We obtain a value, true or false, for every element of the input vector, x. This works because the true-false vector has the same length as the vector that we select from. In this example, we said that we want to output the first number, we do not want to output the second number, we do want to output the third number, and so on. To give us something to select from, we're going to use integer division. The notation %% gives the rest of the division by a certain number. For instance, for the division by 2, we obtain the following. When the rest is 0, the number is even, and when the rest is 1, the number is odd, by definition. To get a logical vector with the even numbers, I can say x %2 equals 0. I get 2 when the rest is 0, that is to say when the number is even. Now I can use it as a selection for getting the values of x that are even. I can change the conditions to get other selections, like the numbers that are 3 times something plus 1. Now, what if I want the numbers that are 2 times something, and also 3 times something plus 1? The solution is to use the logical operator AND, which is that symbol here. I put the two conditions separated by AND, and to make it clear, I isolate each condition by round brackets. I obtain the 4 values of x that are both 2 times something and 3 times something plus 1. Instead of AND, I want either or, I would use the logical OR operator. It's the vertical bar symbol, which on most keyboards is close to the Enter key. I obtain a bigger list because there's only one condition for the number to be in the output. The logical operators AND and OR are really useful when we want to make elaborate selection conditions. Another interesting thing about selecting with logical vector is that sometimes some numbers could be missing. I'm now creating an example with 1, 2, 3, 4, NA. The vector x has 5 values, but the last one is missing. And now let's look at the result of the operation x less than 3. We obtain true, true, false, false, NA. The NA carries through to the result. But what happens when I use this for logical selection? You can see that we get 3 elements, 1, 2, and the last element, which is NA. So when you have missing value in your data, the selection procedure keeps them. So what can you do if you want to remove them? In such cases, you can use the function which. When you call which on a logical operation, you get the indices where the condition is true. Instead of getting true and false, here we get 1 and 2. Those are the positions where x is less than 3. And as you can see, the positions of the NAs are not returned. I can then use the output of which for a selection which is no longer based on a true-false vector, but on a vector of indices. When there are NAs in the input, the function which will remove them when you use it for selection. But when there are no NAs, it doesn't make a difference whether you use the function which or not. Using logical operators and potentially combining them with the function which allows you to make elaborate selection on any vector. Finally, I would like to talk about a way that you can prepare nice documents using RStudio. I'm going to demonstrate the basic properties of R Markdown. To create an R Markdown document, open RStudio and go to the top left corner. Choose the menu R Markdown. This may take some time, as shown by the spinning wheel here. The first time you do this, you may need to install extra packages. If this is the case, click Yes. The install process then starts, and it can take a few minutes. As soon as this is finished, you're asked to fill in the basic information about the document. I'm using the extension .RMD that stands for R Markdown. I like my default output to be PDF, but I can choose HTML or Word. You then get a new panel with a pre-filled document. There is a header with the information that you have just filled, but you can replace it at any moment. You can see some blocks of R code which follow that particular syntax here. The information in curly braces specifies that this is R code, gives a name for the block, and gives some option for the inclusion of the display. There is also a green play button that you can press if you want to run the whole block in the console below. When you do this, the lines are moved and executed. There are also blocks of text in a language that's called Markdown. This is a pun on markup, which HTML stands for. Markdown is used on many platforms like Wikipedia or Stack Overflow. It allows you to format the text a little bit. For instance, these 2 stars here say that the text has to be in bold. The first block of our code did not output anything, but the second has an output. And as you can see, the output of this command is included in the document. And when the output of the particular command is a plot, it is also included in the document. In that case, a PDF of the figure is simply included in the flow of the document. At that stage, you just need to replace the pre-filled commands with your own and the pre-filled text with the one that you like, and also add the blocks of our code that you need. You should of course save your document regularly. If needed, give the right to RStudio to modify your file system. To create a nice looking output of the document, go to the option Knit above. You can choose to create an HTML, PDF or Word document. I'm going to go for a PDF. The rendering takes a few moments. When the document is ready, you can visualize it. You can see that the title and the date have been filled in, and the outputs of the commands are present in the document. Also note that the blocks with equals false do not show the commands that were used to produce them. This allows you to include figures without having to show the lengthy commands to create them. R Markdown has become the standard way of sharing documents when they're prepared with R. It is a very simple way to keep your code tidy and share it with others. That's all I wanted to share with you today. Good luck with the quiz, and see you at the lecture.